If you add random noise to a clear signal, we look for a precise mathematical law that governs exactly how fast the uncertainty grows. De Bruijn's identity provides this answer, offering a surprising link between the raw chaos of entropy and the structural precision of information. This concept isn't limited to a single formula. It represents a spectrum of deep results across mathematics, from calculating information flow in communication channels to counting sequences in combinatorics. The identity always bridges structural properties with precise quantitative laws. In its classical form, we examine a signal corrupted by Gaussian noise. The identity states that the rate at which entropy changes is exactly half the Fisher information, proving that the speed of uncertainty is directly dictated by how well we can estimate the signal. Researchers have pushed this boundary far beyond simple Gaussian noise to include complex systems with sudden jumps. For instance, in fractional Brownian motion, the identity adapts with a specific scaling factor, revealing how memory within the noise alters the entropy rate. Beyond the continuous world of probability, this framework extends elegantly into the rigid structures of discrete mathematics. In combinatorics, the identity helps count perfect cyclic sequences, where every possible pattern appears exactly once. Meanwhile, in number theory, it shifts form to the Dikman-de Bruijn function, describing the asymptotic density of integers that have only small prime factors. These theoretical bridges have concrete operational consequences for modern technology. We use these bounds to design sharper signal estimators for communication systems and to assemble complex genomes using de Bruijn graphs. From the noise in a wire to the distribution of prime numbers, de Bruijn's framework reveals the hidden unity connecting disparate fields. To explore more about these mathematical connections, visit emergentmind.com.